Alright guys, so thank you for tuning into this Cadence digital design video. So in this video, we're pretty much just going to give you the basics for what you need to know to get started with digital design, and more specifically, how to start with schematics and simulation for the GPDK 45 nanometer process. So this video is made for a Texas Tech University class, ECE 4310 and 5310, but the content that we're going to cover here is going to be useful for a lot of different people, especially if you're trying to get started with digital design in Cadence Virtuoso, and even more so if you're using the GPDK 45 nanometer process, since that's specifically what we're going to be using. We're going to be able to see the quirks and details specifically for that process. Now, this video will also assume that you have Cadence Virtuoso installed, and it's also going to assume that you have the ability to run the Virtuoso command and then see the CIW window here. So typically when you're installing or trying to get Virtuoso up and running, getting this CIW window that I have here is going to be your measure for success. So once you are able to run the Virtuoso command, you see this window pop up, then that's a good sign that you're along the right path to getting Virtuoso started. Now, specifically for the Texas Tech class, if you see this GPDK is loaded, that is your true measure of success. So you need some setup files, some CDS environment files, some CDS init files, some Assura files, things like that. And we have those for you. And what I've done to those files is I've added just a brief line to where if you have the files loaded, meaning that you have your Cadence environment set up correctly, then when you first run Cadence, it'll say GPDK is loaded. So now every time that you first open Cadence and the CIW window pops up, you should expect to see GPDK is loaded. If you don't see that, or if you don't see that sentence, if you don't see that line, then what that's going to mean is that you don't have the setup files and that it's going to create issues down the line. So make sure that we have this GPDK is loaded here if you are in the Texas Tech class. Now the CIW window here, it's going to kind of be the center point of what we use, so we're going to come back to it quite a bit. We can see that by itself it's not super useful. So we have what kind of looks like a terminal down here where we can type in, we can run some commands, but we can see it's not very good for digital design, especially if we're going to try and connect transistors and things like that together. So to actually start a digital design library, we need to first open up a new window. So what we're going to do is we're going to press Tools and then Library Manager. And what this does is this opens the Library Manager window. So now we can see we have three columns. We have Library, Cell, and View. On the left-hand side, you can see I have several libraries, so I'm going to have more than you just starting off because I've worked with this PDK before, I've made some reference designs and things like that. But what we do want to see is we want to see Analog Lib, we want to see Basic, and we want to see GPDK 045. So Analog Lib and Basic, those are pretty much coming with Cadence, and that's going to have some very simple things that we're going to use later on, like voltage sources, VDD and ground connections, things of that nature. And then we also have GPDK 045, and this is going to be all the process-specific transistors, inductors, capacitors, resistors, and things like that. So this is what we're going to need for this class, and we can see we've got a lot of different cells, and then each of these cells is going to have a few different views. But we don't want to just start modifying the design files, because modifying the design files means that if we send a design out to the foundry, they're going to say, this isn't what we've gave you to work with. You need to make your own designs using these libraries and these cells. So what we need to do first, and what I'm going to do here as well, is I'm going to make a new library. So you can kind of see the library is kind of the highest point in the hierarchy. So it's going to be a library is kind of an all-encompassing thing for a design. So if you're going to tape out a digital device, then maybe you start off with a library, and then every library is going to have multiple cells, and each cell can have multiple views. And we'll dig a little bit more into that as we get started. So for now, what I'm going to do is I'm going to press File to create a new library, hover over New, and then click Library here. Now, whenever I click Library, a new window will pop up. Pretty much, we just want to pick a location where we can save this library. So I'm just going to save it right here. Up on the top, I'm going to name it AC Tutorial Library. So Tutorial Lib, but you can name it whatever you want. So you typically want to be descriptive. If you're going to make something like a RISC CPU, then you may want to name it RISC CPU. If you're going to make an ALU, you may want to name it ALU, something like that. But you just want to be descriptive, because typically this is going to be a collaborative effort and you don't want people to look at your library and say, what the heck does this mean? But for me, since I'm doing this just for a tutorial, I'm going to name it Tutorial Lib. And then here we're just going to press OK. Now, a new window pops up. I'm going to move it over into the recording window. A new window pops up about a technology file. So a technology file is going to be what this library uses in order to pretty much determine what rules it needs to follow, what we're restricted to, and things like that. So we don't want to make our own. We want to attach to an existing technology library. So we're going to make sure we click Attach to Existing Technology Library. Double check, triple check, because this needs to be correct in order for your library to work. Press OK. And then a new window will pop up asking us which one we want to attach it to. So we want to attach it to GPDK 045. So if we're attaching it to GPDK 045, that means it's going to use the same technology library and it's going to apply the GPDK rules to all of our designs, which is very important. So then we're going to press OK. Cadence is a little slow, so sometimes it'll hang up a little bit. It may take some time. I'm going to go ahead and just press OK one more time. Yep, so we can see it's working down here. So we're just going to have to wait for it to finish working, creating the new library, and then once we have this new library up and running, then we're going to be able to start making cells. Okay, and then we'll take a closer look at what these cells are here in just a moment whenever the library loads. Okay, so now that that process has completed, what we can see here is that now I have a new library named AC Tutorial Library. And this is going to be, like I said, pretty much the hierarchy or the highest point for any project. So if you're starting a new project, you're typically going to use a new library. Now, we can see that we don't have any cells, we don't have any views, and the reason for that is because we haven't made any cells or any cell views. Now, pretty much the hierarchy is going to work something like this. So a library is going to contain many different cells, and each cell could be like a standard function, something like that. So you may start with just an AND gate, or sorry, a NAND gate, NOR gate, and an inverter, and then using those three, you can build up something more complex, or maybe you even have more compound gates, you have D flip-flops, things like that. And you can use each of these cell views to create higher and higher cells that accomplish more and more complex processes. So typically the cells are going to start very simple, and then they kind of grow in complexity later on once you have more tools at your disposal. So here what we're going to do is that in order to make a schematic, we need to have a cell and we need to have a view that is schematic. So in order to do this, we're going to press File, hover over New one more time, and instead of Library, we're going to click Cell View. Now, the new cell view window, we need to make sure that we're under the correct library. The cell, we can name it whatever we want. So for us, we're going to start off with an IV curve. So I'm just going to say IV sim. And I'm not being very descriptive with this because this is not going to end up being part of a larger process. But if this was going to be like an NMOS or a PMOS, you could describe it there. But since we're mainly just using this as an educational tool, I'm just going to keep it as IV sim. Now we need to make sure our type is set to schematic, since that's what we're going to start off with. And then pretty much we're just going to press OK. Now there may be some windows that pop up here. You can just, what I like to do is just keep pressing enter whenever these windows pop up. And then what we will see is that eventually what's going to happen is a schematic window is going to pop up. So now we have our schematic window. It's still working on loading. So the time that it can take for Cadence to respond depends on a lot of factors. It can depend on the workload of the server. It can depend on your connection, things like that. So because of that, it typically works best if you're on Texas Tech property, so you're connected to the network. It's a little bit closer versus having to use a VPN. And if you can, also a wired connection may work even better. But what we have here is now we have a blank schematic window. I'm going to go ahead and make this full screen. And what we're going to do for a first test is we're just going to do a quick NMOS, we're going to do a quick NMOS IV simulation. So what we're going to do is we're going to show the NMOS drain current versus gate current. And I'm going to show you guys how you can do that here. Now, schematic works just like a lot of different software. So LT Spice has schematics, KiCad has schematics, things like that. But Cadence, you really have a big reliance on hotkeys. So what I'm going to do throughout this process is just tell you some of the hotkeys that I'm using to try and speed up the design process. Now, right now we just have a blank schematic. So what we're going to use in order to create a component is we're going to use the command I. So if we just press I on our keyboard, you can see that a new instance window popped up. So I means instance, and that's where we add components. Now for our library, what we're going to use is we're going to use GPDK 045, because this is going to be the library that has all the transistors, inductors, resistors, things like that we're going to end up needing. Now for the cell, we have a lot of options to choose from here. Now, particularly, we are interested in NMOS and PMOS, since that's going to be the transistors that we have. So up here on the top, if I just type NMOS, a little drop-down menu comes that kind of lists all the NMOS that we have. So we have some NMOS capacitors, some QNMOS down here. We also have NMOS 2 volt, NMOS 1 volt. Some of these are HVT, some of these are 3, HVT, LVT, natural. So this can get a little bit overwhelming at first. So I want to point you to a resource that we have. So if you're in the Texas Tech class, this is on Blackboard. But one of the resources that we have is the GPDK, generic 45 nanometer reference manual. So this is going to be a good resource for you to use throughout the class if you have any questions or want to dig a little bit deeper on something. So what I like to do is I just like to Control F NMOS, and we can see that we start to get data sheets down here, and it starts to explain what each of these different things are. And we can kind of just step through this. Eventually we're going to reach a table here for supported devices, and this kind of gives us just a quick one-off of what these devices do. So we can see that NMOS 1 volt is a 1.1 volt nominal VT NMOS transistor. So 1.1 volt means that the maximum drain to source voltage is 1.1 volts. Nominal VT just means it's the standard VT. It's an NMOS transistor. We can see for 1 volt 3, it has an inherited bulk. And then for high VT, we have high VT NMOS transistor. And then for NMOS 2 volt, then that is a 1.8 volt nominal VT NMOS transistor. Same thing, it could have an inherited bulk, it could have a native VT, all sorts of different things. But what we're going to be using is just NMOS 1V. So if I Control F NMOS 1V here, then we can see there's a lot of different stuff, but we can eventually get to the NMOS 1V datasheet. And this is going to be the symbol that we'll see here in just a moment. Gives us a little bit more information on everything that this NMOS has. Gives us a little bit more information about the layers and things like that. So I'm going to move this out of the way. And then, like I said, we're going to be using NMOS 1V. And we're going to be making sure we're in the symbol view. So if we try to use another type of view, like let's say AULVS, then it's going to get really upset with us. Or excuse me, maybe not that one. If we try and use like a SPECTRE view, potentially. ACDL. Maybe I lied about it getting upset with us. So we just need to make sure that we're sticking with the symbol view here. So we're going to stick with the symbol view. And then we can see here that there's a lot of different information that we have here. So we can change the length, we can change the width, the total width, fingers, folding threshold, all these sorts of different things. But for now, I'm just going to keep everything as nominal. So what we're going to do here is I'm just going to place this down so I can either press X here to close this window, or I can press, if I press F3, that'll reopen the window. At least it should. Let me press I again. Okay. So what I'm going to do here is I'm just going to press Escape to get out of the instance select, press I again. Now, if we're on this window, we don't want to drag over to click X. What we can do is we can just press F3, and that actually hides the window for us. So I'm just going to place this down right here in the center of our schematic. And now we can see we have an NMOS. So I pressed Escape to get out of the window, and now we have an NMOS. Now, if I press F, what that'll do is that'll zoom into the schematic so that we can see everything, which is pretty handy if we have a larger schematic. So then we can use the scroll wheel to zoom in and zoom out, things like that. Now, what we're going to do is we're going to start making connections here in order to do an IV curve simulation. Now, to do a simulation here, we're going to need some voltage sources, something to provide power. And to do that, I'm just going to press I again. And instead of using GPDK 045, we can, let me check, basic, and we can check for VDC. Okay, so basic has a VDC symbol, but we can see it's a little not quite what we expected. So we're going to stick with analog lib. And then we are going to be hunting for VDC. So there's a lot of different overlap between basic and analog libraries, but each of them are slightly different, and we're going to stick with analog library because that's what we're most familiar with. So if we stick with analog lib and VDC symbol, then we can get a DC voltage source that we can place here in our schematic. So I'm going to go ahead and place two. I'm going to place one that is going to go to the gate of this NMOS, and another one that's going to go to the drain of this NMOS. And I'm just going to set them down here, press Escape to get out of that instance select. And now we can start wiring things up. So we know that, for example, we need to have this connected to the gate, have this connected to the drain, have all these things kind of connected to a common ground so we can start doing this wiring. Now, to do wiring, you can either go to Create and then Wire, or you can see here we can just press W to start doing wiring. So we can press W. Give it a moment just to catch up to us. And now we can start connecting these terminals together. So I can start with this terminal here, maybe drag it all the way over here, connect the two, take this one, drop it down. We can see that whenever we make a junction here, it adds a little dot for us to know that it's connected, so that's nice. We can connect our body. We need our body to be connected to ground because this is an NMOS transistor. And then we're going to connect the drain to our VDS voltage source, and our gate to our VGS voltage source. So now we've done a little bit of work. We've got it wired up a little bit. Now, one thing we'll notice is that we never really told it what the DC voltages for each of these sources needs to be. Now, one thing we could do is we could click it. We can press, I believe, Q. Yeah, so Q will open up the properties window. And we can add in a DC voltage here. So if we wanted to test out 0.5 volts, we can type in 0.5 and then tab away, and we'll see that it'll add a millivolts here for us, and that's 500 millivolts. We could also type in directly like 250 M, press tab, and it'll add the volt for us. But one thing that's going to be handy for us later on is if we actually define everything in variables, because then we can control everything from a simulation window, which makes it really, really nice. So we don't have to go back to the schematic, change something, and then resimulate. We just stay on the simulation window. So what I'm going to change this to is I'm just going to say VGS and then press tab. And we can see it adds a volt there for us. I can press apply or OK. And we can see that now it says our VDC is equal to VGS. Now we can just do the same thing here. Click on this other one, press Q to open up the properties window. And then this time we're just going to say VDS here. We're going to VDS, OK. And now we have VDC equals VDS, VDC equals VGS. We've defined all the parameters for our NMOS transistor. But for example, if we wanted to change the length or width, we could come over here, press Q on it again, and then change the finger width. So if we want to do 240 nanometers, we can see it already updated some of the other properties here for us, or we can keep it back at 120. Notice how this next line will change immediately for us, so that's pretty nice. And we can use this essentially to change the properties of the transistor. So if you're making an inverter, something like that, you need to change the size of the PMOS transistor. This is how you'll do that. Now, one thing that we haven't done yet is we haven't either saved our schematic and we haven't excuse me, check to see if everything is accurate. So we can actually do that at the same time. So up here at the top, we have a tool. So we have a save icon here, a floppy disk icon that we can click to save, and that'll go ahead and just save our schematic. But a more useful test is to save and check. So the floppy disk with a check mark over it is our save and check. And what this will do is it'll pretty much check all of our connections to make sure that we don't have anything floating. So right now we can check and save. You might have heard that little sound. We can check our CIW window where it'll say schematic check completed with no errors. That's a great sign. Okay, so we don't have any errors in our schematic. Let's say, for example, though, I forgot to connect the body. So I just highlighted the wire, press delete, or you can also press delete and click the wire. So if I forget to connect our body and then save and check, it's going to say that there is now a warning. So it says you forgot to connect this body. You need to check this and make sure that it's connected. So the save and check is going to kind of be our first line of defense into making sure that our designs work. So we need to make sure we save and check before we do any sort of simulation, because it'll throw an error at us later on down the line. So just make sure that you save and check periodically to make sure that your design is working well. Now, one other thing that we need to add here is if we're going to do a DC simulation, one thing that it does need to know is where 0 volts is. So if we don't tell it where 0 volts is, it's going to assume, and we may not want it to do that. So what we can do to tell it where we want 0 volts to be, or our ground to be, is just to add a ground connection. So I can press I, and Analog Live, I can just type in GND, and that'll open up this little ground flag here. And I can just place that down right here. And that's going to always make it to where this is 0 volts here, this is our ground, and that just helps the simulation to ensure that it makes more sense. So now I can save and check. Hopefully everything works well. Can check the CIW window here. So if we check the CIW window, schematic check completed with no errors, and it was saved. So that's a great sign for us. Now, what we can do from here is this is just our schematic, and we usually want to test and make sure that it works before we do anything else like a layout. So what we can do is we can now press launch, and then we're going to launch ADEL. And this is going to be our simulation environment here. And this is going to open up a new window. It's also going to open up this license window when it's figuring out what license to check out. So you can just keep pressing enter, enter, and then eventually we just have this window up and running. Now there's a couple of things we need to check. You may have also noticed that the schematic window changes. So whenever we have this ADEL window up, the schematic window will also change to include some simulation stuff. But there's a couple things we need to check at first. So one of the first things we need to check is going to be the setup. So we're going to go to setup. We're going to check simulator/directory/host. we want to make sure that we have SPECTRE selected here. So we're going to use SPECTRE for this class. There's HSpice-D, Ultrasim, but we're going to be using SPECTRE. That's what we're going to stick with. Okay, so we just need to make sure that is selected. Now we also need to make sure our model libraries are included. Now, one thing that's pretty handy is that we have it set up to where typically the model libraries are going to be included by default. So in this case, we can see that I have GPDK something 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 models, and we just need to make sure we have this GPDK 045.scs. Now we also need to make sure that the section is correct. So MC is for Monte Carlo. We're going to use the TT section. So that's going to mean whenever we're doing simulation, if we want to test how it works with some process variations and things like that, TT is going to be typical, but we can also check out fast, slow, slow, things like that, just to make sure that our designs are robust to the transistor process errors. So here we're just going to press OK. Now, let's make sure we got everything here. Okay, great. So now, one of the first things we can do is we defined these design variables in our schematic, VGS and VDS. One of the first things we can do is just copy them from the cell view. So I right-click here on the design variables window, click copy from cell view, and now we have VDS and VGS. So for now, I'm just going to set both of these to 0.5. So, or I can also do 500 milli, just press enter here. And this is going to pretty much assign 500 millivolts to each of these values. Now, I could press this play button over here, but we haven't told it anything to simulate yet. So it doesn't know if we want to do a DC simulation or a transient simulation, anything like that. So what we need to do is first click over here, and we are going to do so we're going to click here to open up the analysis window, and we're going to choose the DC analysis. So for IV curves and for the transistor, or excuse me, inverter like characteristics, we're going to be using DC analysis. Now we can just press OK here to start off. And what this will do is this will do the DC analysis. We're going to wait for it to pop up here in this window. Let's see. There we go. Okay, so I guess we needed to click enable here down here. Okay, so we're going to wait for this DC analysis to pop up in the window. We also, if we need to make an edit, we can just double click here, and we're going to make sure we save the DC operating point and press OK. So your analysis window should look like this. And now if we run it, it may take some time because it has to open up a new window. So we should see a SPECTRE window open up. I'll drag that over if it opens up off the screen. Expand it slightly just to see everything. You'll also notice that whenever it's kind of locked up and doing some computation on the server side, your windows kind of become a little unresponsive. So this is kind of just something we have to deal with, unfortunately. But now what we're going to be doing, maybe we can check in on the CIW window to see if we're getting any progress. Yeah, so we can see we're getting some progress here. So it's starting up the simulation. Lapse times 0. Zero warnings, things like that. Okay, so it's looking good. I'm going to minimize some of these. And we're just going to have to, like I said, give it some time in order for everything to run and kind of get settled and things like that. So we're just going to give it some time and wait for it to get settled. All right, so we've just reached the point where our simulation is finished, but we can see that we don't really have any results right now because we just did a DC simulation. But one of the ways that we can annotate what's going on in the circuit is by either starting off from the simulation window, going to results, annotate, and then we can annotate the DC node voltages. And then what we'll see is that on our schematic, it'll annotate the voltage at every single point. So it's pretty symmetric right now because we only have 500 millivolts. But if we go back to this window, we can do results, annotate DC operating points. It'll also show the current, VDS, GM for this, the current going through each of these transistors, so on and so forth. So we can use the annotate tool just to show the DC operating point, and that's going to be at this nominal point defined by here. What's often the case is that we usually want to see results in a line graph. So we want to see our DC results versus a certain parameter or a design variable. So what we can do is we can start off by double clicking on our analysis, and then for our sweep variable down here, we're still going to save the DC operating point, but for our sweep variable, we can actually sweep a design variable. So what we're going to do here is that we are going to sweep the variable VGS, and this is pretty much going to determine what's on our x-axis. So if we select VGS, we could either type it in here, or we could select design variable from this new window, select VGS. And then we're going to start, let's start from 0, and we'll stop at 1 volt. And then for sweep type automatic, we could define linear logarithmic. We can define the number of points we'd like to do, things like that. But for this, we're just going to keep it as default. You can press OK. And now we've added a few more arguments to our analysis. So once we have these arguments added, what we can do now is we can press the play button one more time. And then that's going to restart the simulation, and it's going to simulate this circuit versus that VGS value. So it's going to start off by simulating with these nominal values here, and then simulate for the whole range of VGS values that we defined here. So while this is simulating, again, we're just going to let it run. Depending on the workload of the server, it could take some time. And this is just going to, like I said, it's going to depend on a case-by-case, even a time-by-time basis if it's a time-based workload. So it's kind of just something that we have to accept and just wait back and wait for the simulation to finish. Okay, so now that this simulation is finished, we can see that we still have the same results shown here because our annotations only depend on what we have in this section. But if we want to see those line results or the results versus VGS, what we can do is we can click on results and then do direct plot and main form. This is going to be where we do a lot of our 2D plotting. So it's going to open up a visualization and analysis window first, and then it's also going to open up a second window, this one here, where we're able to select the plotting mode, the analysis, and then what we want to plot. So what we'll do is we're going to keep it as append. You can also keep it as replace or a new sub window or a new window, but we'll just keep it as append for right now. And what we're interested in is current. So we're sweeping VGS, and we are interested in the drain current here. So what we're going to do is we're going to have it to where we select a terminal. We don't care about differential terminals, so we're going to select a terminal, and then we are going to check add to the outputs. So that way it's always going to keep what it is that we do, and if we update like the transistor parameters, it'll change accordingly. So now what we are going to do here is we can see down here it says select instance terminal on schematic. So you can come down here back to our schematic, and we can pick an instance terminal. So if we are concerned with the current going into a terminal, that's the way it defines it, the current going into a terminal, we can click the current going in here, and that's going to be our ID. Now we'll see it's highlighted, but if we go back to that window that we just had, we'll see that NMO or NMO/D is not a saved output. And the reason for that is that it doesn't save every voltage, every current. It does save every voltage, but it doesn't save every single current because that could be cumbersome, it could be repetitive. So instead, we can get a little creative. So over here, if we trace the current going into this, we can go back. It's the same as the current coming out of this terminal from VDS. And we can also come right back. It's the same as the current going into this bottom terminal of this VDS source. So instead of selecting this guy, we can select this one right here. We should see that there is now an ellipse around it. And that ellipse means that we are plotting this output. And now we can close this window. And we can go back here, and what we can see is that whenever our VGS is low, we're not drawing much current at all. As we get higher and higher, however, we start to draw much more current. So as our VGS gets to about 1 volt, then we can get up to drawing about 40 microamps or so. So this is going to be how we can start doing these IV simulations. Now I'll keep this window open. We can go back to the simulation tool. One other thing that we can do is that we can use, we may want to see multiple curves on one plot. So what we can do to enable this is that we can actually use a tool called parametric analysis. So right now we can only define one variable to sweep on our x-axis, but we can actually define a second variable to repeat the simulation multiple times. So this is done with VDS equals 500 millivolts. So if we wanted to do 250 millivolts, 500 millivolts, 1 millivolt, then what we can do is we can go to Tools, Parametric Analysis, and then once this window opens up, it's going to open up a new window where we can select more design variables in order to sweep. Oh, sorry, it's opened up already. I just didn't see it. So what we can do here is that we can now add a variable on this left-hand side. So we are going to select VDS. It's telling us its current value is 0.5. It asks us if we want to sweep it. We do. And let's sweep it from 0.25. Well, actually, we might as well start at 0. So we'll sweep it from 0 to 1. And we can either define the linear steps. We can define it as linear. So it's really entirely up to you. I'm going to keep it as auto, however. And then for total steps, this is where you have to be pretty good at counting. So if we want to do 0, 250, 500, 750, and 1 volt, then we have to do 5 total steps. So that'll be 250 millivolt steps from 0 to 1 volt. Now, we don't want to come back here and click this guy because this is just going to run our single simulation. What we want to do is we want to click this new play button in our parametric analysis window here. And that's going to open up an entirely new progress bar here that we have to monitor. So we should see that open up here in just a moment. The HPC server's been really slow today, so we're kind of having to slow down quite a bit in order to accommodate for it. But what we should hopefully end up seeing is that there's going to be a progress bar right down here. Okay, so now we can see that we have our progress bar starting here. We can also see that the CIW window is starting to update. So like I mentioned, the CIW window is a great tool just to see if there's anything updating. If something's not working, typically it could spit something out in the CIW window to give you more information why that is. So it's a really good tool to just always go back and look at. So I really want to just hammer that in, that the CIW window, even though we don't do a lot of the design from there, is still a very useful tool. And that's kind of the main way that Cadence speaks to the user, is through the CIW window. But now what we can see is that this parametric analysis is beginning. So we can see up here it first set VDS to 0, then it did the netlist. It's comparing the design with the netlist just to make sure everything is accurate. And then it's going to continue this simulation process for every single one of these steps. So because of that, this could take some time because the HPC server is slow. So we're going to do another jump cut in order to save time in this video. But what we should see is that this progress bar is going to incrementally increase. So because we have 5 steps, it's going to increase in 20% steps. And as it increases, this is pretty much going to be telling us how far along in this parametric analysis we are. Now, what you're going to see is that this progress bar moves considerably slower than the one at the bottom of our simulation window here. And that's because of the fact that it's having to do this progress bar several different times. So that's something that we're going to see. So typically, if you're going to try and do like 101 steps, it's going to take a really, really long time. So it's generally good to do something like a much coarser step in the parametric analysis window versus a very fine step, since a fine step could take a really long time. So I'm going to, again, step back. We'll do another jump cut, and we'll jump back in whenever this progress finishes, just to see what the results look like. All right, guys, so the parametric simulation has just finished up. And like I said, so what we're going to be using this for is to sweep a secondary variable so we can see like how the change of one variable can affect our results. And since we left our window open and we have our current saved to our outputs, we don't even have to change anything. We can just go right back to our results window. Now, obviously, as we can see, when VDS is 0, we're not going to be drawing really any current whatsoever. But then as VDS increases, we're going to draw more and more current for the same VGS. So this kind of helps to visualize how you can do something like an IV curve. This isn't exactly something you'll have to do in your homework for the TTU class, but this should give you kind of the resources that you need in order to tackle an IV curve for an NMOS and for a PMOS. Now, I want to show you just a little bit more so we can get like a slightly more complex schematic. It's not going to be very complex, but just to show a little bit more on how you can use this DC simulation and how you can use it to kind of get some practical results for digital design. So I'm going to actually close almost everything here. So I'm going to close our results window, our parametric analysis window, and then on this side, if I want to come back to this ever, I don't want to have to redo everything I just did. So what I can do is I can just do session, save state, and then in this new window up at the top, I'm going to click cell view just because it's typically a little better for SPECTRE to click in the cell view, because then you can just double click this state from your library manager window and it'll automatically open it for you. And then we just want to make sure everything is clicked. Press OK. It could take some time because we're working on a slower server right now. And then we're going to ask if it wants to overwrite. We're going to say yes, OK. And then now in our library manager window, we can see that there's now a SPECTRE state 1 that we can come back to and open. So we can just go ahead and close our ADEL window. And then I'm also going to close the schematic window because we're pretty much done with this schematic here now. So what we're going to do now is we're going to come back to our library manager, and then we are going to make a new cell view now. So I'm just going to show you how to make a simple inverter. So we're going to do File, New, Cell View again. And then instead of it being an IV sim, I'm going to make INV. So just a shorthand for inverter, makes it easier in the future to pull this up if I need it. And then make sure it's a schematic, press OK. I'm going to kind of move through this a little bit faster this time because we've already kind of seen everything that we may need in order to do this. So what we're going to do here is once our schematic window opens, to make an inverter, we're going to need both an NMOS and a PMOS here. So once our schematic gets fully loaded, we can press I. We don't want analog live, we want to use GPDK. Press tab, and I can actually just go ahead and look right now for NMOS 1V. We're going to keep the symbol, and we're going to keep it just at unit length, unit width. And I'm just going to click this down here. Now, from this side, I still have an NMOS selected. If I want to get that instance window open again, I could press I, but what happens is that the instance window is kind of minimized, or it's behind our schematic window, so we'd have to manually go over and click back to it. Well, what you can do is you can press F3 once, that'll close the instance window, and then press F3 again, and it'll open it right back up for you. Now here I can press Shift Tab to go back up here, and instead of NMOS 1V, we're going to use PMOS 1V. So this is the PMOS counterpart to the simple NMOS that we used before. We can see that its length and width are still the same, and we can just put this right here on top of this guy. Now, we're going to still need to wire everything together here, so we're going to wire it just in a simple inverter scheme. So we're going to have the gates connected together. We're going to have the source of the NMOS connected to the body. Both of these will eventually be connected to ground. Same thing, the body of the PMOS is going to be connected to the source. Both of these will eventually be connected to VDD, and then their drains will be connected together, and we can actually add just a little line here to go further out to kind of separate it, make it seem that this is our output. Same thing, we can do the same thing with our input, kind of just draw it a little further away so we know, excuse me. So I accidentally right-clicked, we can hit escape there though. Now we can add a couple of other things here, so we can add an instance. We're going to go back to analog live now. We're going to use ground. We're going to add a ground symbol here. And then the counterpart for ground is VDD. So here we can also go back to the top, add VDD, and then now it's just our VDD symbol up here at the top. Now, it doesn't know what voltage we want to give it, so we still have to give it a VDD or a voltage source in order to power on these transistors. But this should be okay just for now. So for our input, what we're going to do is instead of VDD, we're going to use VDC in analog live. We're going to add this right to our input. And then we're going to add another voltage source over here that's eventually just going to be our power, and we'll come back to that here in just a moment. Now, each of these needs a ground. It needs to know what the voltage is in reference to. So what we can do is we could just open up the instance window again, add a ground, but what's easier to do is we can just click this guy, press C to open up the copy window. May take some time. I believe it opens up a window here, maybe not. So we can see we have this new image in front of our mouse. We can just click on ground and it'll copy ground. We can bring it right over here. So same thing, we can press C, copy, bring it over here. We can press F3, and there are some options that'll be presented to us. So if we need to make like an array of copies, we could do that. But we don't really need that for now. We're just doing simple copy and paste. Now, like we said, this is going to be our VDD voltage source. So we also need to tell it that this is connected to VDD. So VDD really just assigns anything that's touching this VDD point is connected together. So instead of us having to manually draw a wire from here to this point, excuse me, let me delete this. So instead of having to manually draw a wire from here all the way over to here, we can just use VDD, and that'll help keep our schematics a little bit cleaner. Now for our VDD voltage source, we can click it, press Q. For our DC voltage, I'm just going to call it VDD, lowercase VDD. You could also call it maybe chit VDD, something like that. But for us, I'm just going to call it VDD. Now Control D, if we have something selected, Control D will deselect everything. So if I have this clicked, I need to click over here, we could press Control D to deselect it, or we can just click over here. Now we're going to press Q, and we're going to call this one VN. Okay, so now our input voltage is VN. We have VDD powering everything on. Now, if we save and check right now, it is going to kick back a couple of warnings. or just one warning here. And the reason we have a warning is because this is not connected anywhere. So it's just floating. It doesn't know what we want to do. It's not going to break anything. We can still run a simulation, but it's not nice to have these little warning markers here on our schematic. So what we can do, press I to open up the instance window. This is actually under the basic library. And what we're going to be looking for is just a cell called no con. And it's a cell that looks like this. And all it's going to do is it's going to pretty much flag a net that tells it doesn't need to be connected. Now we can use the rotate command here to rotate our symbol around to make it look a little bit nicer. And we can just add it right here. Press escape to get out of our instance window. Now I can save and check. And we shouldn't have any warnings, any errors, anything like that. So yeah, now our warning has disappeared here. We can check the CIW window. We can see that there are no errors, no warnings, anything like that. Now we can do that same process where we launch ADEL. So we're going to keep, pretty much everything should be defaulting to the proper value, but if you're going to be meticulous about it, you can go and check. We can copy in our variables. So for our VDD, we're going to set it to be 1 volt. For our VN, we can just start with 0.5. And now for our DC analysis, I'm going to assume that we kind of learned a little bit more about our DC analysis from the previous one. So we're going to click DC, save DC operating point. And for the design variable that we're going to sweep, now we're going to sweep VN. So we're going to sweep VN, and what we're going to do is we're going to measure the output voltage based on these different VN values. So we expect that if VN is 0, our output is going to be VDD. And if VN is VDD, our output is going to be 0. So we're going to sweep it from 0 to VDD, and then we can just keep our sweep type as automatic. Now if we press OK here and try and simulate, I'm not going to do it right now because it could create an error later on, but what we're going to end up seeing is that this would create an error because it doesn't quite know what VDD is. So what we need to tell it is we actually need to put something in here. I believe it is par VDD, not capital, par VDD. Oops, excuse me, not par, it's var, VAR. So Cadence is pretty good about letting us know whenever we make a mistake. So now we can press OK. And we can just see it's not going to kick back any errors. Press OK. And now we can just click and run this simulation. So like I said, it's taking some time for me right now. So instead of making you guys wait for this to simulate, we're just going to monitor the CIW window. And we will come right back whenever this finishes simulating. All right, so now that our simulation has finished, we can see we haven't told it what we want it to plot yet, so we don't see any results. But to do that, we can just click Results, Direct Plot, and Main Form. So here is going to be our visualization window, and then the new window should be popping up shortly that I can drag over. So now we have our plotting mode. We're going to keep it as a pinned. We're still using a DC analysis here, except now we want to see what the voltage is. So we're going to go ahead and click Add to Outputs and then select a net on the schematic. So on the schematic, I'm just going to click this net here, our output net. We can see it highlighted as green, so that's a good sign for us. And now we can come here, click our results window, and we can see that it's behaving pretty much exactly how we would expect it to. So what we're seeing is that whenever we have a low voltage input, our output is now high. Same thing if we have a high voltage input, our output is now low. So this is behaving pretty much exactly how we would expect and want an inverter to behave. And if we zoom in a little bit further, what we can see is that when our input voltage is at 500 millivolts, so right in between the two, our output is slightly too low. So again, this is because the NMOS is going to have a lower resistance. So the NMOS material is going to be a lower resistance, or it's going to present a lower resistance, so it's kind of overpowering the PMOS. So if we wanted to balance this and try to get it as perfect as possible, we can go back to our schematic, play with these PMOS parameters here, change the width slightly, increase the width. Oh, excuse me, so when I try and click this guy, we hear a little error sound, and the reason for that is because we still have this direct plot form open, so we need to close this. Now we can click on this guy, press Q. We can change some of the parameters here to try and make it so that it is more balanced and that they're pretty much equal, symmetric. But that's going to be something that you guys are going to have to do yourselves. So you can use parametric analysis. You could try and define a variable. For example, you could make the finger width here, you can make it M times 120. And then later on, we'll see that it changes some of these because now we have a variable inside of our, a variable inside of our equation, or a variable inside of our properties here. But you can use this in order to try and sweep different values for the width, see what would work out the best. Okay, so one other thing to notice about the width is that if we try and increase it just slightly, like 121 nanometers, it doesn't like that whatsoever because it can't control it down to 1 nanometer. Potentially, if we increased it up to 140, then it does like that. If we tried 135, it's okay with that. If we try 133, for example, it doesn't like that. So it looks like it's in 5 nanometer steps, so you can increment it. So maybe we could do 125 nanometers. You can kind of play with this in order to figure out what would work best for this inverter in order to make it so that it is as balanced as possible. So again, looking back at these results, we can see it's not quite balanced yet. We're a little slightly off. If you want to make this look a little bit better too, one thing you can do to change these, the way these results look, you can click on this line. You can right click, trace properties. Oh, excuse me, not trace properties, that's my fault. So we can click on this line, right click, and we can change the width down here. So right now it's set to thin. We can set it to medium, thick, and extra thick. So if we try extra thick, then we can see that we can now see these results much more clearly. So if you need to take a screenshot and submit it with your homework, for example, this is probably a little bit better to make sure that whoever's looking at it doesn't need to squint to really see the results and the curves and things like that. Okay, so this is just to give you guys, like I said, a simple introduction to how to use the schematics, how you can use DC simulations, voltage sources, all these other things, and also how you can use parameters inside of the SPECTRE simulation in order to actually, in order to actually see how the circuit behaves in DC terms across a wide range of operating conditions. So that'll pretty much be it for this video. And the next video is what we're going to be looking at is how we can use these schematics, how we can make symbols for them so that we can actually use our schematics that we've made in bigger schematics, because oftentimes we don't want to have thousands of transistors in a single schematic. That can get very confusing. Instead, it'd be nice to define some basic blocks like inverters, AND gates, and then use those building blocks to make something more complex. And that can be done using symbols. In the next video, we'll also take a look at transient simulations, since those are another very good way of seeing how things like delay can impact your circuit. So how different circuit parameters can impact delay and how you can optimize them. So that's going to be for the next video. That'll be all for this one. I appreciate you guys watching. If you have any questions, please feel free to either email me or leave a question in the comments below. I'm more than happy to answer any questions that you guys have. So again, thank you for watching, and I hope you guys enjoyed it.